Hello, my name is William Greim, and this is my video paper review of computational methods for playing games. All papers discussed in this video were found via IEEE Explore using search terms such as computational methods for playing games, machine learning games, as well as searching for specific games that I thought might have a few research papers on, such as chess, StarCraft 2, Mario, the Snake game, etc., etc. Alright, so here I'm going to display the abstract that's been written for each of the papers. I'm not going to read them word for word, I'll just do a short explanation, but if you want to read them, feel free to pause. Paper 1 is implementing the chess engine using NNUE with the Negamax algorithm. So this paper presents a chess engine that integrates the NNUE, or efficiently updatable neural network, with the Negamax algorithm, which is just a variation of the Minimax algorithm that allows for negative numbers, to improve decision-making efficiency and strategic depth. The problem tackled is enhancing traditional engines like Stockfish by leveraging NNUE's dynamic evaluation of piece values and a Negamax algorithm's simplified feasibility comparisons using both positive and negative values, which reduces computational load. The engine, called Stockdory, was tested against Stockfish using historical games from Lasker and Alkaline. Results indicate Stockfish excels overall, particularly in traditional positional games, but Stockdory showed potential in certain metrics like evaluation speed, indicating future promise for growth in computational chess. Paper number 2 is titled A Deep Q-Learning-Based Approach Applied to the Snake Game. This paper proposes a deep Q-learning approach to train an AI agent to play the Snake game. The problem addressed is creating an effective agent capable of optimizing game performance without complex visual inputs, relying instead on sensor data for state representation. The deep Q-learning model uses a neural network with 5 fully connected layers to approximate the Q values for various game states and actions. The training involves reward-based learning, where the agent improves by maximizing rewards from eating fruits while avoiding collisions. Key hyperparameters were tuned, with the best configuration yielding a mean score of 56. This approach demonstrates promising results for high-performing agents in real-time games without image processing overhead. The main paper we'll discuss is entitled Adaptive Average Exploration in Multi-Agent Reinforcement Learning. This paper introduces an adaptive average exploration method for multi-agent reinforcement learning, aiming to improve agent performance and training speed in StarCraft 2. The key methods include the adaptive average exploration action selection technique, which adjusts the exploration rate based on team win ratios, and transfer learning to accelerate learning by reusing previously learned knowledge. Adaptive average exploration was tested against traditional epsilon greedy exploration in the QMix algorithm. Results show that the adaptive average exploration achieves more stable and efficient learning, while transfer learning further enhanced performance across similar combat types. Frequent exploration updates also contributed to stability, outperforming conventional approaches in multi-agent tasks. Right? So this paper looks to improve performance of multi-agent reinforcement learning in StarCraft 2 by using adaptive average exploration over the traditional greedy epsilon method, while also utilizing transfer learning to speed up training between different unit types within the game. Multi-agent reinforcement learning is a branch of reinforcement learning in which a group of agents work together to maximize their rewards as a team. The goal of the multi-agent reinforcement learning algorithm is to learn effective strategies for defeating the opponent within a set interval of time. To achieve this, the QMix algorithm is used to ensure that agents learn cooperatively and consistently. QMix traditionally uses the greedy epsilon method for exploration, where 1 minus epsilon is the probability that the model will take the optimal action, and epsilon is the probability that the model will take an explorative action. The researchers do test the greedy epsilon method in this research paper, just to get a baseline for the adaptive average exploration. 2 different decay rates are explored, rapid and slow decay. The rapid decay quickly decays the value of epsilon from 1 to 0.05 in just 10,000 time steps. This allows the agents to very quickly prioritize the exploitative actions that they've learned. Slow decay decays over 10, epsilon decays over 100,000 time steps in slow decay. This encourages longer exploration, but potentially delays high reward actions. And then the update values for epsilon are listed here below, and epsilon is updated every 200 time steps. Right, so adaptive average exploration is the process of dynamically adjusting the epsilon value based on the performance of agents over time. We use the troop's win ratio between episodes to adjust epsilon. Tests include intervals ranging from 5, 20, or 100 episodes for update. This balances out the agents attempting to take the best-known approach with exploring new approaches. So when win rates are high, the values of epsilon will decrease, encouraging agents to exploit the tactics that they've learned work well. And when win rates are low, the value of epsilon increases, encouraging agents to explore new tactics. The agents use the QMix algorithm for training. QMix allows agents to make global observations during training and local observations during testing. This allows the agents to learn tactics that are optimal for their team, and then operate independently during testing, meaning they naturally make team-positive decisions during gameplay without global observations. QMix also combines individual agent reward values into a global Q value. This Q value is monotonic, so agents performing well will never reduce the global Q value. Again, this rewards the team for team-based tactics. Agents can earn points by damaging and destroying enemies. At the end of the round, if all enemies are dead, a large bonus is earned. So those local observations they'll make during testing involve the distance of the enemy, relative X and Y position, health and shield, and unit type of the enemy. During training, global observations consist of coordinates of all agents relative to the center of the map, all agents' local observations, and histories of all agents' last actions. Each agent is controlled by their own neural network. During testing, each agent has a limited field of view, so all actions are based on the viewable environment. The discrete actions that they are allowed to take are moving in the cardinal directions, attacking, stopping, and no operation. Transfer learning experiment will test transfer learning with the following enemy types. Each type has a different style of combat. So you have the Marines and the Hydralisks, which are both ranged, and you have the Zealots and the Zerglings, which are both melee-based units. So the researchers do use transfer learning to help agents generalize the strategies that they learn and to speed up training across different combat scenarios. The combat scenarios involve the baseline Marines versus Marines, as well as the transfer learning Marines versus each different type of enemy that we listed before. It's a 3v3 in each case. The metrics for success are the jumpstart value, which is the initial performance boost seen from the previous training, the time to threshold, which is the time it takes to reach a given threshold of performance. In this case, it is 0.8 is the performance threshold for win ratio. And asymptomatic performance, this represents the difference in performance between the transfer learning agents and the non-transfer learning agents. The way it works here in the experiment is that units are trained in combat for 500,000 time steps before the agent networks are saved, and then the networks are trained for another 500,000 time steps against the native StarCraft 2 AI to complete their training. Alright, so for each experiment, they will consist of 5 training sessions. Each training session will be 500,000 time steps, during which agents will take an action, receive a reward, and make observations. One episode will be 60 time steps, or whenever all Marines on a team die. For the testing phase, after 10,000 time steps, the training is paused and epsilon is set to 0. This means that agents will be taking the optimal action only for those time steps. The percentage of episodes 1 will be called the test win ratio. Again, feel free to pause and look over specifics and the diagrams that are on the slide. I won't be going over all of them. But for the greedy epsilon experiment involving the fast and slow decay rate for epsilon, we saw that the slow decay method for epsilon was superior in win rate stability over time, despite the testing win rate being unstable at the start. The lower win rate and stability seen in the rapid decay method can likely be attributed to the agents having less time to explore actions before being forced to pick the optimal action, meaning agents had fewer optimal moves, if any, to choose from. Adaptive average exploration results, the 20-episode case, resulted in the most stable long-term performance, despite the 100-episode epsilon update rule having an early advantage. The 20-episode update rule also had the best variance among all tests, further solidifying the clear advantage in performance and stability of win rate. The worst test case by far was the 5-episode update rule, having neither an advantage in learning rate or performance. The average episode length was 24 time steps, meaning that the episodes very often ended well before the 60-second timeout, and that all enemies were eliminated rather often. If you want to pause the screen and go ahead and look over all the metrics for the transfer learning results, that's totally fine. I'm not going to go over all of them just because I'm running short on time. But for the transfer learning results, we saw that performance was primarily boosted between units with similar combat types. All transfer learning test agents outperformed the non-transfer learning Marines, except for the Zerglings, which further highlights the importance of the training scenarios to be somewhat similar to see much of a performance boost, as the Zerglings are melee-based, unlike the ranged-based enemies that they trained under. So to summarize, for the greedy epsilon decay rate, we saw that the slow decay rate was superior in terms of steady win rate growth, variance, and consistent long-term performance. For the adaptive average exploration results, we saw that the 20-episode update rule was optimal between the 5, 20, and 100 update rule for the learning rate and low variance. We also saw that the 20-episode update was comparable to performance in the greedy epsilon testing. And for transfer learning, we saw that the agents showed improved jumpstart and time to threshold metrics, especially in ranged versus ranged combat scenarios. Transfer learning definitely accelerates performance gains, especially for similar combat types, underscoring the performance for aligning transfer learning tasks with the original training. Future work could extend these techniques to more complex environments, such as aerial combat scenarios, to further validate their effectiveness in diverse settings. All right, and that is the overview of my chosen papers. These are my references. Have a nice day.